In 2014, volunteer crews along the Louisiana coast hauled burlap bags of cured oyster shells down to the waterline and stacked them one by one into the shallows. Louisiana was losing its coastline faster than almost anywhere on Earth. The answer came from restaurant scraps. 17 million pounds of oyster shells dropped back into the water, building over 10,000 feet of living reef. Then the shore held. Every night, after the last table cleared, restaurant workers in New Orleans wheeled bins of spent oyster shells to the back alley. Trucks collected them before dawn. The shells went to landfills. That had been the pattern for decades. The shell that once armoured Louisiana's shoreline was being buried under garbage instead. Tons of it, every single week, from hundreds of kitchens across the city. Meanwhile, the coast was coming apart, not slowly, catastrophically. The marshes that buffer communities from storms were dissolving into open water. Engineers had poured years and genuine fortunes into the problem. Concrete barriers, dredged sediment pumped back onto eroding banks. The coast retreated anyway. The coalition to restore coastal Louisiana looked at the landfill trucks and saw something different. Not waste, raw material. The exact material the shoreline had been losing for generations. The process had 3 stages. Shells were collected from restaurants. They cured in open air for 6 months, long enough for bacteria to die off completely. Then volunteers bagged them and carried them to the water. A cured shell dropped into the Gulf does something concrete does not. It recruits. Juvenile oysters, called spat, settle onto the calcium surface within weeks and begin cementing themselves down. Each generation of oysters builds on the last. The reef grows upward and outward. It absorbs wave energy. It traps sediment. It does for free what the concrete never managed. The object on a dinner plate in New Orleans and the structure holding the state's shoreline together, they are the same object. Louisiana just had to stop throwing one of them away. More than 6,000 volunteers have carried shells to that waterline the reef they built, now stretches across what was open, retreating water. But the engineers who spent decades on concrete had data. They ran the numbers, and the reef was doing something their models had not predicted. What the engineers could not have predicted was the scale of what had already been lost before a single bag of shell hit the bottom. This was not a coastline under pressure. It was a coastline in the process of erasing itself. Most people scanning the Louisiana coast from a boat see marsh grass, brackish shallows, and a horizon low enough to touch. They are not looking at a coastline. They are looking at the ghost of one, a living shell-armoured edge that spent decades quietly vanishing. In Lake Pontchartrain, the nearshore beds that once broke incoming wave energy had been commercially harvested to near nothing. The bottom was bare mud. Every storm drove wave action straight into the marsh edge, unimpeded, unbroken, unchallenged. Along Bayou Bienvenue, the wetland buffer had collapsed so completely that open water had replaced what was solid ground within living memory. The land did not flood. It ceased to exist. And the people whose families had fished its edges watched it go. At the Vermilion Bay margins, what remained of the marsh grass was undercutting from beneath. The root mat, the last physical anchor holding the land in place, hung exposed to full fetch with nothing left to absorb the swell before it arrived. In the Pontchartrain Basin, the shell hash that once carpeted the substrate, the rough calcium-rich surface that juvenile organisms need to grip, had been buried under decades of fine sediment. There was nothing for a spat to attach to. No structure, no grip, no interruption. This is the part that made me stop and reread the field notes. The biological armour was not being destroyed by the sea. It had been removed by hand, plate by plate, season by season, decade by decade. And nobody had been putting the raw material back. A reef interrupts a wave before it reaches the marsh. It forces the swell to spend its energy on structure rather than on soil. Remove that structure and the soil goes, slowly at first, then at a pace that swallows a football field of land every single hour in the worst hit parishes. Louisiana was losing land at a rate that ranked among the fastest coastal erosion rates recorded anywhere on Earth. That number is not a projection. It is a measurement of what was already happening while the shells piled up in landfills across the city. And yet the restored structure, once it went back in, was doing something to the sediment column that the programme's biologists had not written into their recovery timeline. The rate of change was not what anyone had modelled. It was faster. And the mechanism behind that speed is not yet fully understood. The rock breakwaters went in first. Engineers drove barge after barge of quarried stone into the Gulf margins, calculating load tolerances and wave attenuation with the precision of people who had never watched the Gulf decide it disagreed. Within a few seasons, the silt found the gaps. The Gulf did not assault those structures. It simply moved around them, depositing fine sediment in the lee, undermining the footing from beneath, burying the base until the rock sat in mud and the water kept going where the water always went. Synthetic reef mats followed. Prefabricated concrete panels lowered to the substrate at enormous cost, designed to mimic the surface complexity of a natural reef. They held their position. They just never grew. That is the essential difference. A concrete mat sits at exactly the size you placed it. Same footprint next spring, same footprint a decade later. An oyster reef recruits new animals onto its surface, and each one adds shell mass to the structure without a budget line or a crew. After a storm strips material from a concrete mat, it stays stripped. After a storm moves through an oyster reef, the surviving animals spawn into the disturbed zone, and the next cohort settles onto the exposed substrate. The reef repairs itself by reproducing into its own wound. The engineering logic was not wrong about materials, it was wrong about time. It assumed that durability meant staying the same. A living system does not stay the same. It responds, it recruits, it compounds, and compounding is the one thing a poured slab cannot do. Here is the part that should make every coastal engineer pause. The programme's biologists and the engineers paying attention already knew the biological mechanism worked at smaller scales. The unresolved question was whether you could source the raw material entirely from the city's waste stream, cured on a parking lot, bagged by volunteers, and build functioning reef at a scale that actually moved sediment. The answer came back in the monitoring data. More than 10,000 feet of living reef had been built without a single paid dredge contract. No heavy equipment. No quarry invoices, no mobilization fees, just cured restaurant shells and volunteer labor. The shell on a restaurant plate in New Orleans and the barrier holding the state's edge together are the exact same object. Louisiana just had to stop throwing one of them away. That reframing, waste as infrastructure, is what the hard engineering model never found room for in its cost tables. What the sediment data showed next, The rate of accretion building in the lee of those reefs, parish by parish, is where the numbers stopped behaving the way any of the models predicted they should. The accretion rates the field teams logged were not gradual, parish by parish. The land behind those shell lines was holding at margins that outpaced every projection the hydrological models had published. It begins at the bottom, a bag of cured shell lands in the shallows. And within weeks, free-floating larvae, spat, no larger than a grain of sand, drift down and make contact with that hard calcium carbonate surface. Bare mud offers them nothing. The calcium carbonate of an existing shell is the only surface they will accept. That is the first lock in the sequence. The substrate calls the animal into existence here and not somewhere else. As those spat grow, their shells build physical relief into the bottom. Ridges, gaps, pockets of texture. That texture slows the water. Slowed, water drops its suspended load instead of carrying it seaward. The sediment falls into the gaps and builds the foundation from beneath, while the reef grows upward at the same time. Then the reef reaches the height where it intercepts wave energy before that energy reaches the marsh edge. The grass behind it, which had been undercut by open water fetch for decades, stops retreating. The root mat of that grass stabilizes. The soft edge of Louisiana, or the edge that was converting to open water, finds the first physical reason in a generation to hold its ground. Not policy, not funding, physics. The stretches of shoreline where that living structure now runs are measurably more intact than adjacent unprotected stretches. Same wave exposure, same subsidence pressure, same gulf. One difference, the shell on the bottom. The reef did not just armour the coast, it rebuilt the physical conditions that allow a coastline to exist at all, one shell at a time. No motor running. What no model had anticipated was the compounding. Each new generation of spat settles on the shells laid by the generation before it. The reef is not a static structure you place and walk away from. It is a construction site that runs itself. The question that now sits with every coastal program watching Louisiana is whether the same sequence, substrate, spat, texture, sediment, stabilized marsh, can be triggered with the same economy of means somewhere that does not already have a city full of restaurants to source the raw material from. The fishermen noticed it before the field crews did. Working the near-shore stretches adjacent to restored sections, they were pulling up species they had not seen in that water in years: red drum, sheep's head, blue crab, animals that require vertical structure and shadow to hold territory. Nobody designed a fishery. The program's goal was coastal defense. Hold the marsh edge, slow the land loss, buy the state some time. The crevices and shaded undersurfaces of the restored structure did something the engineering brief never included. They recruited an entire community of finfish and invertebrates that had no reason to congregate in that corridor before. This is the part that no coastal model easily handles. A structure built to absorb wave energy becomes simultaneously a productive fishing ground. The habitat complexity that makes it good at one job makes it irresistible for the other. The oysters built the architecture. The architecture called the fish. The fish arrived without an invitation and without appearing in any line of the original budget. What makes this complicated is exactly what makes it remarkable. A restored stretch that holds the shoreline in place also shifts the local catch. And that shift crosses property lines, changes where commercial boats run their routes. and raises questions about governance that a coastal engineering program is not automatically equipped to answer. The program's community engagement work had to grow alongside the restoration itself. Landowners adjacent to restored sections began asking who manages the fishery the reef attracted. Fishing families working those corridors wanted a say in where future restoration work goes. A conversation that began as "Can we hold the coast?" became "Who owns what the coast now produces?" That tension between a coastline defence and a fishing ground is not a failure of the programme. It is evidence that the restoration exceeded its own scope. The structure worked well enough to generate outcomes that the original plan never had to govern. Every coastal programme now watching Louisiana has to sit with this. You can plan the substrate, you can count the volunteer hours, and the tonnage returned to the near-shore zone. You cannot fully plan what a functioning living structure calls to itself once the conditions are right. And that unpredictability runs in both directions. The shell that held the coast also fed the community beside it. The question now sitting in every coastal office, from the Gulf to the Chesapeake, is whether a programme born from restaurant scraps and volunteer weekends can be translated into formal policy before the next stretch of shoreline quietly becomes open water. Louisiana did not engineer its way out of a crisis. It returned a material the coast had always depended on, let the biology do the rest, and watch the outcomes multiply past the plan. What happens next depends on whether anyone else is willing to start with what their own restaurants throw away. Every state that borders the Gulf has watched something shrink. A sandbar, a marsh edge, a line of grass that stood at the same place your grandfather fished. The mechanism behind that loss is not mysterious. Remove the hard substrate, and the soft sediment behind it has nothing to hold it in place. What Louisiana demonstrated is that equilibrium is recoverable. Not everywhere, not instantly, but wherever the missing material goes back in, the physics of the place resumes. The water slows, the sediment settles. The biology reads the new conditions and responds to them. That is not optimism dressed up as science. That is what equilibrium means. A system returning to the state its physical conditions have always preferred the moment the pressure that displaced it is removed. The shell was never waste. It was the coast, disassembled one dinner plate at a time. Tell me where you live, and tell me one thing you watched disappear from that shoreline. One species, one feature, one sound at dusk you stopped hearing and stopped expecting back. Drop your region and one species you have personally watched disappear from your area in your lifetime. And yes or no, in the comments, have you ever seen something come back that you were certain was gone for good? Because if the answer is yes, I want to hear that story. Share this with someone who still believes the damage is permanent, because the evidence says otherwise. A reef that began with restaurant scraps and volunteer weekends is now a measurable barrier between inhabited land and open water. In the Chesapeake Bay, native oyster restoration began reversing decades of water quality collapse. Turbidity dropping in reef zones, submerged grasses returning to channels that had gone dark for a generation. But the Army Corps of Engineers resisted large-scale reef construction for years, arguing in formal review that ecological benefit did not justify reallocating bottom leases from commercial harvest to conservation. The same species that filters the water drives a commercial industry, and you cannot fully restore one without changing the economics of the other. That tension has no clean resolution. It has only a direction, and the direction the water is moving in makes the argument for one side louder every year. The shell is already there. The shoreline just has to stop losing it. One reef, one estuary, one changed policy at a time.